Hello everyone, my name is Aditya Tiwari, Assistant Professor, CSVTU Bhilai. In this tutorial, we discuss the operation inside the M-way search tree. In the previous tutorial, we already discussed what is M-way tree, what is the role of multi-way tree, what is the order of M, and how we design this M-way tree, or how it will be an upgraded version of a binary tree or the AVL trees. So already such type of work already discussed in the previous tutorial. So today we discuss the operation in M-way search tree. One operation is like as you know that the operations are in data structure like searching, insertion, deletion, traversing. This kind of operation we perform everywhere. Searching operation we already done in the previous tutorial. Today we discuss the insertion part and the deletion part. Before starting the insertion, you're already having some tree like that, this one. With this example you can understand. Here we having a lot of items. This is a 5-way search tree. It means maximum you producing a child from any generation, that is called a 5, as well as the maximum keys available at anywhere is a maximum is a 4. So as we know that if order is 5, so maximum keys are the 4, that is equal to the children minus 1, that is a key. So each and everywhere in all the generation, all the children's, all the root node, everywhere in the leaf node also, you can insert maximum 4 keys anywhere. If you increase more than 4 keys, that will not satisfy the property of this M-way search tree. As you know that M-way is completely depend on the order of M. So here we having a order of M is a 5, that's why the key supporting value is only a 4. You can insert a 1 key also, but a maximum key is a 4. When you're inserting any element, any data inside that key, you have to cross check. You don't increase not more than the 4 keys anywhere in that tree. So first we insert a 6. Here we having a tree already available, like in a root node we having a 4 items like 18, 44, 76, 198. As per the binary tree, all the smallest items are connected in that the left hand side of the children of any key, and the biggest item are connected as a right successor of any key. As you see, 7 and 12 both are lesser than the root node 18, that's why both items are connected as a left successor of 18. As well as 8 and 10 both are less than 18, but both are greater than 7 but less than 12, that's why it should connect in between 7 and 12 keys. That's why he follow the path at the right successor of 7, or we can say the left successor of 12. There are both item 8 and 10 are connected with the middle children of a 7 and 12. In a same phenomena, all kind of the data item are connected as per the respected places. Like 262 is a greater of all the root items like 18, 44, 76, 198. 260 is greater than 198. That's why it should connected as a right successor of 198. As well as 272, 286, 350, all are the bigger, or we can say larger than the value of the root item, as well as the current right successor of 198, that is a 262. That's why 272, 286 and 350 all are connected as a right successor of 262. Same phenomenon 80, 92, 141, then 148, 151, 172, 186, 77. When you connected any item, you have to cross check the in order successor should be followed. If the sequence of in order sequence is not coming after you inserting any elements inside that tree, it not follow the property of the M-way tree, or we can say the binary tree. As I told you, M-way tree follow the property of B tree as a sequence of in order traversal, but only one changes, you can insert more than 2 childrens in a tree that's completely depend on the order of M. That's why the name of the multi-way tree. So by this diagram you understand the concept, how we insert an element, and we should to follow the tree of in order traversal also. When you find out the in order sequence, the sequence are in the all our data in the ascending order. So you can't skip, no the bigger item will come in the middle position or smallest item will come on the right position, is not follow. So now we insert item 6 in this M-way search tree. So first we have to cross check with the root item. The first item is 18. We compare our new item with the already available item, that is 18. Here we see 6 is less than 18. That's why our pointer will be shifted and move to the as a left successor of 18. Here we are having a left successor 7 and 12. Again my new item 6 is compare, first we compare with the 7, then we go for the 12. But here again we check with the 7, 6 is less than 7. 6 is less than 7, it means my pointer will be not moving somewhere, it should be find out the place. If there is a facility to insert an item at there or not. If space is there, definitely we insert a new item 6 as a neighbor of 7. Otherwise we connect to as a left successor of 7 also. In a multi-way tree you have free to insert a new item, either a neighbor place, either as a left successor, either right successor also. In a child format you have to connect it, or either a neighbor also you have connected item in that multi-way tree. So here we check 6 is less than 7 and 7 having a 2 probability to insert where one is a neighbor of 7 as a left neighbor of 7 as well as the left child of 7. So that is completely dependent on you. You can insert, you have to free to insert that new item in anywhere as either a neighbor, either a left child. Here I insert as a left neighbor of 7 because we having a space as a maximum order, the MWay is of 5. Here we having only 2 items 7 and 12. We can insert 2 or more item in that particular case where already 2 items are available and the new item is requesting to insert as a neighbor of 7. We easily insert that new item as a neighbor of 7 in a particular place. So we can't go for the as a left successor of 7. So we easily insert 6 as a neighbor of 7. After inserting a 6, you have to again do cross check the tree is a MWay tree or not. Yes, the tree is MWay tree because after inserting a 3, only 3 keys are available and the 4 childs are available. That's why after inserting a 6, multi-way tree follow the property of MWay tree. So the maximum order of key is a 4 and here we insert only 3 keys. That's why it tree is definitely completely supporting to the property of MWay tree. Now we are inserting a new item that is called a 146. So again, if we fix a pointer at the root node, at the first element of the root node. Here we are having a first element root node is 18. My pointer will be fixed at there and again cross check with the new item and comparing with that item. The new item is 146 comparing with the 18. 146 is greater than 18. Then pointer will be shifted to the right neighbor of 18. Here we are having a right neighbor of 18 is 44. Pointer shifted at there. Now again cross check with the new item. Again my new item is greater than the pointer item. That's why again pointer will be shifted to the right neighbor of 44, that is a 76, and 76 again is less than the 146. So our new item is greater than the pointer item. So again pointer will be shifted to the 198. Here we check. Here we see 198 is greater than 146. It means the new item 146 should be connected in between the 76 and 198. Either we connected in between 76 and 188, or either we go for the as a right successor of 76 or we can say as a left successor of 198. First we try to insert that new item 146 in between the 76 and 198. Can we insert? No, here we don't insert this item because 18, 44, 76, suppose we insert a 146 and then 198. So after inserting a 146 as a neighbor of 76 as well as a 198, but after insertion of 46, the root node keys are 5, which is not supporting this order of M, because when you're inserting a 146, the children producing value is a 6, which is not supported this order of MWay search tree. So we can't insert this new item in between the 76 and 198. So we go the another way to insert that item by the children of 76 and 198. The both common children of 176 and 198 is as a right successor of 76 and left successor of 198. So we go fix our pointer at where? At the children of 76 and 198, that is a 80. So 80, 92 and 114 both all are the children of 76 and 198 as well as. So we fix our pointer at the item of current successor that is called a 80. So again we compare with the new item 146 with the pointer data is a 80. Again 146 is greater than 80. That's why the pointer will be shifted to the current next neighbor, that is a 92. Again we compare, again new item is greater than 92. Again pointer will be shift to the right neighbor, that is called a 141. Again we compare that particular item, 146 is greater than 141. So here I will go for the connection of the 146 as a neighbor of 141. But the problem is that here we are having a space. The space is not an issue. In the previous one, space is an issue, but here we having a space because 80, 92, 141, only 3 items are available, only 3 keys are available. Definitely we can connect a new item as a right neighbor of 141 in the form of 146. But the problem is that when we connected 146 as a neighbor of 141, so all the item 148, 115 which are connected previously as a right successor of 141. When you connected a 146, it means 148, 151, 172, 186 all are lie in between the 141 and 146 child. That is not satisfy the property of in order traversal sequence. So we can't insert 146 as a right neighbor of 141. Space is a okay, but the problem is that the in order sequence is not fulfilling when we inserting a new item 146 as a neighbor of 141. So we can't insert 146 in this place. So in that case again we take a help from by the children. So we call the children or right successor of 141. So why right successor of 141? Children are 148, 151, 172 and 186. And again we take a help to insert that new item at the position of right successor of 141. My pointer will be fixed at the position of 148. Now again we compare with the new item, previously item, that is a 148. Now my 146 is less than 148. So it should be inserted as a left neighbor of 148. If we insert a 146 as a left neighbor of 148, so again space is an issue. So we can connect it, but space is a play an important role, because after insertion of 146 the key values will be a 5, that is not supporting the particular of this tree of 5-way M-way search tree. So maximum you can connect it a key, there's a 4 items are already available in a form of 148, 151, 172 and 186. So we can't insert 146 as a neighbor of 148. So we go to then again we take a help as a children of 148. So before previously 148 having a left child is a null. Now we connect a new item by replace of null and we pass the address of that new node, that is a 146 node. So we pass the address as a left child of 148 and 146 should be connected as a left child of 148. So this is a way, somewhere having a space issue, somewhere having a connection issue, somewhere having a larger in order traversal sequencer issue. So lots of problem when we connecting and when we inserting a new item into a M-way search tree. But M-way search tree give you freedom to either you connect it as a left child or as a right child, either you connect it as a left neighbor, as a right neighbor. That is completely depend on the two things. One thing is a space. If a space is there, no issue, you can connect your item as a neighbor also and as a left or right neighbor also. Second one is after you connecting that item, the in order traversal sequence should be satisfy the property of this tree. If in order traversal sequence is not satisfied, so we can't connect that particular node, particular item in some places. So you have to see, too much serious about when you're connecting a new item in a M-way search tree. This is a way how we connect a new item into a M-way search tree. I hope you understand how we connect, how we perform an insertion operation in a M-way search tree. Now move on the next and the last operation part, that is called a deletion. Deletion in an M-way search tree. So last operation, the most important questions, insertion, deletion, somewhere in universities question paper, question examinations, lot of time there such a question arises from the M-way search tree in an insertion part as in the deletion part. So we move on the next part is a deletion part. So deletion in an M-way search tree, let's K. We can understand by the example. Let's K it means key. K be the key to be deleted from the M-way search tree. Here we having a k, and k having a two children like in a form of ai and in a form of aj. So ai is a left successor of k and aj is a right successor of k. It means ai items are less than as compared to a, and aj item are greater than as compared to k, and both are the pointers to subtrees of particular key values. Now, when you go for the deletion operation, you having a four cases you have to check. First one, if suppose you want to delete a key from any place, and that the key having children ai and aj, and ai and aj both are null. The first situation. So first situation is that if ai and aj both are null, this is a very simple case. When you deleting, when you going to perform or delete to any key which having ai is also a null, it means no left child, no right child, we can easily remove that particular key from the m-way search tree. So we easily delete that particular key from the m-way search tree. Nothing will be happen inside the only removing that particular key from the m-way search tree. Rest of the item, rest of the tree are as it is same. So nothing to worry about when you deleting any key which having no child, like a leaf node. Now second one is when you going to delete a key which having a ai is not equal to null and aj equal to null. It means the right successor child are the null. There is no child at the right hand side, but some children are available as in a form of left successor of particular key. So when you going to delete that particular key, it should be replaced by the children, and the children you choosing the largest of the key element k dash in the child node pointed to by the ai, and replace k by the k. Suppose you having a 10 as a key and 10 and as a left successor are the 4, 5, 6. You having a 3 items 4, 5 and 6. When you deleting a k from the key, it should be replaced by the largest key dash value, the child value, and amongst the 4, 5 and 6 the largest value is 6, and 6 we should be replaced by the 10. So this is a way when you disconnecting or when you removing or when you deleting a key value, and the key value should be replaced by the children, either a left, either a right, but in this case, second case, the right case is already null. So when you replacing the from the left children, you have to choose amongst of the children the biggest element, and that particular item key will be replaced by the largest value. This is a second case. Now we go for the third case, the vice versa of second case. Now when you deleting an item or a key, and again key having a two children ai and aj, but ai equal to null, it means the left successor items, or we can the smaller successor of items are the null, and aj is not equal to null. It means we having a few items as a form of right successor of particular key. Then in that case we have to go to choose the smallest of the key elements from the k double dash. Here I take a k dash as a left successor and k double dash as a right successor. So we select amongst of the elements. Suppose again we delete one to key as a key is equal to 10 and the right successor having a child like 15, 20, 25. So when we want to delete that particular key, we should to replace by the right child of the smallest value. Amongst 15, 20 and 25, the smallest value of k double dash is 15. So when you deleting a 10, it should be replaced by the smallest value of the right successor child, that is called a 15. So we replace key element from k double dash of the subtree pointed by the aj, delete k from the tree and replace by the either by the k double dash. So this is a third approach when you replace and when you delete an item and should be replaced by the smallest item of the right subtree. Now the last case, this is a little bit complicated case. Above three cases are simples, but in the last case, this is a case when you deleting a key and key both having a childs. AI also is available and AJ is also available. It means A is not equal to null and AJ is not equal to null. AI means the smaller, all the smaller item of the keys as compared to keys are also available. AJ or the greater item as a right subtree of a key is also available. Then choose, either again depend on you. Either then you choose the largest of the key elements from the k dash. K dash is means either you choose the largest element, data element from the left child, or in the subtree which is pointed by the AI, or the smallest of the key element k double dash from the subtree pointed by the AJ to the replace of k. So here having a two option. Either you can replace key from either a left child, either a right child, but you choosing a left child, it should be you take a choose a largest value from amongst of them, and when you choosing the right subtree, you have to select the smallest item amongst of the right subtree of item them. So either you having a facility, you having a freedom to replace key from anywhere, from left child also, right child also, but the condition is one. So if your condition is focus, if you are taking from the left child, taking a largest value, you're taking on the right side, you're taking a smallest value. By this approach, you can replace any key item when you're having a both child in a M-way search tree. By this graph, we can understand, by this operation, we can understand how we delete an item and how we easily delete an item from the M-way search tree, or after deletion, is this tree is follow the property of M-way search tree or not. So we already be having take a same example. So we already had lots of items available in some places in that tree, and that particular tree again is the order of 5. This is called a 5-way search tree. Now I want to delete 151. So before you delete performing a deleting operation, you go for the searching operation. As we already discussed how we go to searching, again we set a pointer at the root node, and also in the root node we fixed our pointer at the first item of the root node. So the first pointer, that is pointer, will be fixed at the item 18. Now pointer data will be cross checked the searching item. The searching item is 151. 151 is greater than 18. That's why pointer shift to the neighbor of 18. The right neighbor of 18 is 44. Again with the compare 151. So again 44 is less than the 151. Now again pointer will be shift to the right neighbor of 44. That's why that is 76. Again comparing. So our searching item again is greater than 76. Pointer data, again pointer will be shift at the 198. So 198, now our searching item is 151 is less than the 198. It means we have to understand the searching item, it should be present in between the 76 and 198. So we follow the path of in between the 76 and 198, or we can say the child between the 76 and 198. So move the pointer from the next generation, or see the next level, that is children of 76 and 198, that is 80, 92 and 141. All are these siblings. So we connected our pointer, we should fix our pointer at the item 80. Again we cross check our searching item with the 80. 151 is greater than 80, that's why the pointer will be shift to the current right neighbor of 80, that is a 92. Now again we compare with that 92, again pointer will be shift to the 141 as a neighbor of 92. Again item is not matched, or again when item is not matched, again our pointer will be try to shift to the right neighbor, but there is no any right neighbor of 141. So we change the generation, we change the level by the as a right successor of 141, and our pointer will be shift to the right successor of 141, that is a 148. So our pointer will be shifted to the largest value amongst the child of 141, that is a 148. So pointer will be fixed at the position of 148. Again we compare with the 148, again item is not matched, it means pointer will be shifted to the current second neighbor of 148, that is a 151. Then again we compare, here our item will be matched. Now you have to cross check the 151. 151 having a two children in a form of AI and AJ. AI should be lie in between 148 and 151, and AJ should be lie between 151 and 172, and both are null. If both are null, this is a first situation. We want to delete any key which having AI and AJ both are the null. It means the left successor and right successor both are null. You can easily remove that element, that key from the MV search tree. Nothing will be happen after you deleting that key which having a no child. Rest item are as it is. They are not relocated. They are already as it is fixed at that particular item. Only one changes 151 after deletion 150 is not available in that tree. By this diagram, next diagram, you can understand 151 is not available in that tree and rest item all are available in the same position. So again, after deleting a 151, all items are there, and as well as follow the property of MV search tree. So this is a first case when deleting any key which having both AI and AJ are the null. Now move on the second case. Second case is talking about we want to delete any key which having any single children's, like that either a left successor is available, either a right successor is available. So in this particular T we have to select another item, that is we have to select 262. So 262 where here you check the 262 is the current right child of 198, and you will see 262 we are having a two children's AI and AJ. AI is equals to null and AJ having a item in a form of 272, 286 and 350. So three items are available as a right successor of 262, but in a left successor of 262 no one is there. That's why the AI equal to null. So AI equal to null but AJ having a item. When you going for this such kind of operation, this is a third type of case when talking about that one. When you deleting any key which having only a single children's items, either as a left successor or either as a, here we having a right successor. So again I told you, as I told you, when you deleting a 262, so you take a help from the, you can't empty from that place. You have to replace that key value by his children. Somewhere some children will be replaced by the 262. So you have to cross check from the right successor, because left successor is not available. That's why we take a help from the right successor. Right successor we having a three items. Again that all three items are connected as a right child. So we take the smallest value amongst of them and replace by the key value. Here we having amongst the 272, 286 and 350, the smallest value is 272. So 272 is replaced the 262 item. So after replacing, the tree will be showing this figure. So 262 replaced by 272 and the rest item are as it is, nothing will be changes, only the two changes. 262 will be move out from the tree and the position of 262 replaced by the 272 from the 200 is taken from the right successor of 262, and 286 and 350 are as it is, only 272 will be upgraded to the move to the up level generation in a form of as a right successor of 198. So this is a way to delete any item which having a right successor or a left successor. So easily you remove the data. Again, this is a one approach where we take our data from the right successor. Now we take another example how we take our data from the left successor if the Aij equal to null and Ai equal having a items. So another operation when you're deleting a 12. So here which again you cross check to 12. 12 again you performing a searching operation. By the same pointer will be 6 at the first position 18. When you comparing that one, 12 is less than 18. That's why our pointer will be shift and fix as the left successor of 18, that is a 7. Again we comparing with the 7. Then again we comparing with the 12. Here item will be matched. So it means pointer will be fixed where at the right neighbor of 7, that is called a 12. Now when we go for the deleting or removing that 12 from the tree, first we have to cross check the children part. So here we having a AI but AJ is not available. AJ equal to null. There's a completely a vice versa case of the last when we deleting a 262. Here AI having an item in a form of 8 and 10 and AJ equal to null. So when you're removing a 12, again you take a help from the children. So one of the children should be replaced that particular item 12 when you're deleting. So again, when you're taking a help from the AI, or AI, as you know, as a left successor of 12, when we take a help from the left successor, we always choose the largest value amongst of them. So here we have got two items 8 and 10. So 8 and 10, the largest value is 10 amongst of them. So 10 it replaced by the 12, and when we replace the 12 by the 10, 12 is automatically deleted or the removed from the tree. Nothing will be happen, only one changes, 12 is replaced by the 10, rest of the item are as it is, you can see in this diagram. So after deletion, the tree is as it is, follow the property of M-way tree. So we can say this is a M-way search tree after deleting a 12. Now problem is that when you go for the deleting any key which having both child AI and AJ. By this diagram we can check, suppose we having 198, suppose we have to select 198 and want to remove that 198 from the tree. Again pointer will be fixed at the root node 18, compare with that one, pointer will be shifted to 44, then 76, then 198. Now item will be matched. So item is matched, it means we have to remove 198 from the tree, but we can't do directly from the tree. First we cross check the children are available or not. So 192 is a special type of key which both having a children, both side children's, AI is also available and AJ is also available. Also grandchildren is also available. That is a very big issue. So in this case, the biggest problem, so when you removing a 198, you having a freedom, either you take from the left side or the right side, both of the places you can take a help. But the question, only one situation, when you're taking a help from the left hand side, you have to choose the biggest value. And when you're taking a help from the right hand side, you have to choose the smallest value. In that case, you have to find out the in-order traversal of particular 198. So when you find out the in-order traversal, you know the in-order traversal is a left, root, right. In that case, the current neighbor of 198 is in a left form, that is a 186, and 186 as a left successor of 198, and the 262 as a right successor of 198. So either you replace by the left successor also, either you replace by the right successor also. The condition is only one. When you're choosing from the left successor part, the item should be a greater amongst of all of them. It means the parent as well as the child also consider all of them and find out the maximum, the greatest value amongst of them. It means here we have been cross checked, 186 is the greatest value, that's why 186 should be connected at there. Or either you can go for the right hand child also, you can take a help. Again you take a help from right successor, the smallest value is at 262 and the 262 will be replaced by the 198 and 272 will be jumped to the 262. So in the same phenomena you can remove any item, any element, any key from the M-way search tree by this operation. Only the last case, that little bit complex when you having a both child in a form of AI and AJ. So when you're selecting a AI, take a largest value. When you're selecting a AJ, take a smallest value. By this approach, you can delete item from a M-way search tree. So here we can understand the concept how we insert a new item in a M-way search tree, how to delete an item from a M-way search tree. There are basically 4 approaches when you're deleting an item from a M-way search tree. One already we cover all the parts one by one, how we delete an item from a M-way search tree. So this is a really no doubt is an advanced version of a binary tree, but this tree also having some complexity, some problems, some issue and some limitations. The problem is that this tree is not balanced tree. So when you inserting any item, when you deleting any item, you can easily remove any item from the tree. You can easily insert an item. There is no need to either you're having a freedom, either you connected as a left child also, as a right child also, as a left successor also, as a right successor also. But there is a, after inserting, deleting, that tree may be a balanced tree. There is no, maybe a balanced tree or not a balanced tree. So this is a limitation of this M-way search tree. This problem is sorted by the this next operation, that the next tree, that is called a B tree, that is extended version of a M-way search tree. The name of that tree is the B tree, and B tree is the extended version of the M-way search tree. Like a M-way search tree is like a binary tree, or we can say B tree as a AVL tree. So B tree is an extended version of a M-way tree, having a freedom to insert any number of children in that B tree, any number of items. This again depend on the order, but after you inserting or deleting an item, should be a sequence and should be a balancing. The main thing is the balancing. Balancing should be satisfied after you performing any operation in a B tree. So that tree, B tree, will we see in the next tutorial. So I hope you understand the concept of the M-way search tree, advantages of M-way search tree, applications of M-way search tree, and also we understand the limitation of M-way search tree and what is the drawback. That drawback will be sorted by the next and extended version, that is called a B tree, and this B tree or B plus tree we can see in the next tutorial in upcoming classes. Thank you.